This learning object is provided by the University of Colorado Boulder, and this particular learning object is focusing on blackbody radiation, which is a principle of physics that we cover in thermal physics, astrophysics, and climate change. The university provides many excellent learning objects for science and mathematics, and I have used the learning objects provided by this university to demonstrate many different concepts, use them for design labs, use them for data collection labs, use them for conclusion and evaluation, and basically use them for manipulation. The learning objects provide an excellent way to demonstrate very hard to understand concepts. This particular learning object, or with this particular learning object, students have control over the temperature. Students can see that as they increase and decrease the temperature, the black body curve also increases and decreases in intensity, but also moves from the right to the left, showing a change in wavelength. For this activity, students are going to collect data to prove this, what's called the Stefan-Boltzmann's constant, and also Wien's displacement law. For the Stefan-Boltzmann's constant, students are going to change the temperature and measure intensity values and collect values for intensity. To do this, we select the ruler. We place the ruler next to the y-axis. Students then change the axis to an intensity of 10. Oops, the other way, intensity of 10. And we're saying that the full-scale deflection is 30 centimeters, so for every 3 centimeters is an intensity of 2 megawatts per meter squared. Students can then change the temperature readings and find the temperature at every 3 centimeters up to 10 centimeters, therefore collecting data of temperature and intensity. Students can also, for the second part of the experiment, measure wavelengths against temperature. To do this, they select a wavelength of 1.5 micrometers maximum deflection, and they start taking measurements at around about 0.9 micrometers. To do this, they put the ruler against the curve, where the curve is the maximum peak. They can then record the temperature. If they increase the temperature, the curve moves to the left. They can do the next one will be 0.8, and so forth and so forth. Once they've collected this raw data, they can then use this data to plot some graphs in Excel. The first graph shows temperature against intensity, and it's very easy to see that this is not a straight line, it's actually a curve, so we can't generally get a relationship. But if students then manipulate the data, and they do temperature to the 4 against intensity, they can see that this is a straight line relationship. We have a constant of 5 times 10 to the minus 8, and this 5 times 10 to the minus 8 watts per meter squared Kelvin to the 4 is very close to the Stefan-Boltzmann constant of 4.7 times 10 to the 8. Similarly, with Wien's law, they can do wavelength against temperature, again data collected from the learning object. This again is not a straight line, it's a curve, and students can then manipulate this data to do 1 over wavelength against temperature, again seeing that this is a straight line and getting a constant of 0.003. This is very close to the Wien's displacement constant of 0.0029 meter Kelvin. So hence they can prove that by doing this, manipulating this graph, they found this constant. The idea behind this learning object simulation is that students can physically get a grasp of what these constants are, and by manipulating them using Excel, they can actually prove these constants themselves without actually taking it from a textbook and accepting it. The advantage of this is that it's very hands-on activity. Students see the relationships working directly in front of them, and they can manipulate, and they can collect the data and manipulate the data. This lab activity itself would be a manipulative skills lab, where they follow a set of instructions, and by following these sets of instructions they can start to build this pattern and see the pattern emerge.